All right, honor stats, here we go. This is section 5.2, dealing with probability and compound events. You'll see with compound events, there are two compound events. One is called a conjunction, which uses the word and one is called a disjunction, uses the word or. In so many words, let me just kind of break it up here for y'all. If you have an and, so if we have the word and, I'm going to kind of preface every single thing before we go into the lesson itself. And you're going to have multiple drawings. And that is multiple coin tosses, multiple dice being rolled, multiple cards being dealt. More than one thing, two or more. Events, when it's and, can be independent or not. And you'll have two formulas for and, two formulas. And they actually are basically the same. One of them is the probability of event A and event B is equal to the probability of A times the probability of B. The other formula for A and B, and it can be written twice, the probability of A times the probability of B given A. That's a straight line called given. Notice it started with an A and then the B was the first thing. Or the probability of A and B, this is the same. These two that I'm writing right now are exactly the same. It is the probability of B times the probability of A given B. And it's funny, all three of them are kind of the same, right? You won't even know which one you're using per se. This one, the events are independent. And you simply multiply the two probabilities together. This one is when they are not independent. Right? Some books call it dependent. Some books call it not independent. Goes hand in hand. I was always a not independent type of teacher. And it's funny, because this is read the probability of B given A. It's basically the problems where you do not replace. Like dealing cards. You deal a card, the deck goes from 52 down to what? 51. A little bit different. So in a sense, you won't even know the difference. Okay? So what we just saw here was and. Okay? Let's look at or. I'm going to do the exact same thing for or. And now let's talk about or. Or, ladies and gentlemen, that is when we're dealing with only one drawing. Only one thing is happening. You're choosing one marble out of a bag. You're choosing one card from a deck of cards. Okay? One. These events are mutually exclusive. Or another word we use is disjoint. Mutually exclusive is much neater to use. It also has two formulas. It is the probability of A or B is equal to the probability of A plus the probability of B. We use that formula when they are mutually exclusive. And we use this formula, the probability of A or B, which is the probability of A plus the probability of B, but we have to subtract the probability of A and B. That means if there's an overlap, okay? I'll kind of explain that real quick, okay? Let me do this in red. Okay, let me explain this one. From a well-shuffled deck of cards, I want you to deal one card. That's it, one card. So as soon as we go one, notice my question is going to have the word or in it. And here's my question. What is the probability that that one card is a queen or a king? Queen or king. So as soon as I see the word or, we know this is going to be an addition problem. Notice the difference between the two is this guy right there. That is said for this example, hey guys, can one card at the same time be a king and a queen? No, there's no such card as a king-queen. Therefore, those events are mutually exclusive. So the answer to that question, probability of choosing a queen or king, is simply 4 out of 52 plus 4 out of 52, because there's 4 queens and 4 kings, which is 8 over 52, and all probabilities get reduced, 2 over 13. Now let me give you an example of an overlap one. Ready? You are going to deal one card. What is the probability that that one card is a king or a red card? Wait a second. There are red kings, so there's an overlap. Those two events, king and red, are not mutually exclusive. So we're going to take the probability of a king, add the probability of a red card, but we have to subtract a king and red at the same time. Why? Because we counted them twice. So there are 4 kings, so that's 4 out of 52. There are 26 red cards out of the 52. And then we say to ourselves, there are how many red kings? Heart king, diamond king. So there's 2 of them. We got to subtract, because if you think about it, aren't the 2 red kings here? And aren't the 2 red kings there? You've counted them too many times. So you're taking it away. So this is going to be what? 30 take away, so that's 28 over 52. Take out a 4, 7 over 13. So I gave you a little bit more with or. All right, disjoint, exclusive, mutually exclusive is a little easier to explain. As we continue with this particular chapter, we'll see about the multiplication and a little bit more. Or the events can be mutually exclusive or not mutually exclusive. 2 completely different formulas for those ones. If they are mutually exclusive, you simply add the 2 fractions and you're done. If they are not mutually exclusive, you have to add the 2 fractions and subtract their intersection or their and. That is 5.2. So in this particular section, we are going to compute probabilities of general compound events. That's what I kind of explained. Those are your and your or questions. We're going to compute probabilities involving independent events or mutually exclusive. They're still and or. Just know, independent always deals with an and. Mutually exclusive always deals with an or. And then we're going to compute a conditional probability. And I kind of explained that. That's a probability of A given B and probability of B given A. Okay? And just so you know how it's really read, this is the probability that A occurs given that B has already occurred. That is called a conditional probability. Condition. If 2 events are independent, if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. The multiplication principle is the probability of A and B is equal to the probability of A times the probability of B. Well, if the events are dependent, remember I like the word not independent, then we must take into account the changes in the probability of one event caused by the occurrence of the other event. This is the notation A given B. It's called a conditional probability. So, our formula will change a little bit. Our formula for A and B, notice these are both the same. Here I start with the probability of A. Here I start with the probability of B. Notice they're both multiplication. And this is B given A. So if this is A, this has to be B. If this is B, this has to be A. These are basically the same exact formulas, okay? If they're not independent, you're going to use this formula right here, okay? You're going to use these two formulas. All right, they look a little bit weird, but they're not too bad once you start seeing an example, okay? Or formulas for the conditional probability themselves. If you think about it, everybody, we had the probability of A and B. Sorry, that's the symbol. They have not taught us the symbol, so I have to use the word and. A and B is equal to the probability of B times the probability of A given B. We just had that a couple seconds ago. Well, think about it. If you divide by the probability of B to both sides, then the probability of A given B, which is right here, is equal to this. Well, that's where they got that, guys. They took a formula that you already know and they just kind of solved it for something else. This is your conditional probability formula. A given that problem, given that something has already occurred, given that A happens, given that B has already occurred, okay? You'll see it when we get to the examples. And there's two. So here's an example. I'm not going to go through all the stuff the book does because this is very straightforward. Suppose you are going to throw two fair dice. What is the probability of getting a 5 on each die? See, they didn't really write this the best way. They should have said 5 on first die and 5 on second die. Now, they wrote it the way they were. They wrote it correctly, but you have to see the underlying connector. And, ladies and gentlemen, this is an and question. So, and you have to think of independent. Hey, guys, when you roll that first die and it comes out a 5, does it have any bearing on what the second die is going to do? No. The first die doesn't sit there on the ground and go, hey, second die, become a 5 because I'm a 5. No. That means these events are independent. So, simply, everybody, you have to take the probability of rolling a 5 and the probability of rolling a 5. Guys, how many 5s are on one die? 1. How many numbers are on a die? 6. So the probability of rolling a 5 is 1/6. What is the and operation? Is it plus or multiply? It is multiply. And the other 5 is also 1 out of 6. Multiplying straight across, you get 1 out of 36. And you have learned the multiplication rule when dealing with independent events. And the events can be independent or not independent. Multiplication. I just want to show you this to prove it. They wrote all 36 outcomes for you when rolling 2 die. 1, 1, 1, 2, and so on. And look, there's only one instance where you got a 5 on the first die and a 5 on the second die. 1 out of 36. I think we got there a lot easier. And means thing. Ready? So this is what I was just trying to explain to my class. Whether or not you have independent events or not, when you have independent event, it's simply the probability of A times the probability of B. That's your dice question. One die has nothing to do with the other die. But this right here, actually, think about a deck of cards. And I say getting a king on the first and a king on the second when you're dealing 2 cards. Well, guys, there's 4 kings out of 52. But that card actually has something to do with the next card. Why? Because you already have that card in your hand, so there's 51 cards left. The 4 means you have a king, which means there's only 3 kings. Basically, I'm explaining that. Okay? The die was 1/6 times 1/6. These events are independent because the second die had nothing to do with the first die, or the first had nothing to do with the second. But this card problem, notice when I dealt that first card, it had bearing on the second card. Why? The denominator definitely goes down by 1. It's still multiplication of 2 fractions. It's just events being independent or not independent. And the final, now I explained our addition rules, I think, really well at the beginning. Understanding. So, the addition rules, this is called a Venn diagram, just so you know. The addition and or, what's shaded in right now is and, please, and then particular problem. Questions. Everything shaded in is or. So, or is a big picture. It's everything shaded in of this, okay? Or is bigger, okay? You use addition rules when only one thing is happening, okay? But the events can be mutually exclusive or not. Questions? Okay. So, in this example, we have freshmen, sophomores, juniors, and seniors. And we have some females and some males. There are 31 total students in this particular problem. Everyone see what we have? Beautiful. Freshmen, there's 15. So sophomores there are. Sophomores, there's 8. How many males are there? We have 6, 11, 13, 14. So 14 out of the 31 children. Sophomores, there's 8. Twice. We counted the male sophomores twice. This 5 was part of my 15, and it's part of my 8. So got into question. So now, suppose we select one student. Remember I told you, or has one drawing at random from the class. I bet you $10 the question has the word or in it. What is the probability that a student is either a freshman or, I told you, a sophomore? So before you start this problem, you have to ask yourself this question. Is the event mutually exclusive? Meaning this simple question in your head. Can you have a student that is a freshman and a sophomore at the same time? No. You can't be a freshman and a sophomore. So in your mind, these events are mutually exclusive or mutually exclusive and independent. So you say to yourself, let's see how many freshmen. 15 out of the 31. Probability I'm a freshman or probability I'm a sophomore. Probability of freshman, 15 out of the 31 kids, or means addition. Let's see how many. So sophomore is 8 out of 31. So our formula is simply add the 2 together, 23 out of 31. They put both here just so I can say if I want a decimal, give me a decimal. If I want a fraction, give me a fraction. That's why they have them both there. So it's your job when you have the one drawing and you see the word or to ask the question, are they mutually exclusive? Get our males. Sophomores. Fraction of students, what do we have to take with 8? Well, obviously I'm going to give you a mutually exclusive. Notice here they said everything selected at random will be either a freshman or sophomore. No student can be both a freshman and a sophomore at the same time. But let's do question B. I'll go back to blue. It says, select one student at random from the class. Again, the one selection kind of pushes you towards an or. What is the probability that student either is a male or a sophomore? Uh-oh. I can find the probability of a male. Or means plus. I can find the probability of a sophomore. But everybody, we must subtract any student that is a male and a sophomore at the exact same time. That means these events are not mutually exclusive. Phenomenal. So let's go back. Are males. 14 out of the 31. Let's get our 8 out of 31. But we've done something. We've counted a 5. I said 15, it's actually 14. So 14 and 8, so that's what? That's going to be 7? 8 minus 5 is 3, 17. I don't know why I said 7. 17 out of 31. So you got to get a couple words in your head. When you have an and question, the word independent comes to mind. When you have an or question, mutually exclusive comes to mind. Okay? It deals. So, we say events A and B are mutually exclusive or disjoint if they cannot occur together. This means that there is no intersection. The intersection is 0. The and is 0. So, by definition, two events are mutually exclusive or disjoint if they cannot occur together. In particular, A and B are mutually exclusive if the probability of A and B is equal to 0. Think about a Venn diagram, ladies and gentlemen. This would be event A. This would be event B. Do you see how they're separated? Those two events would be mutually exclusive. There's no overlap. The overlap is the and, okay? If that's the case, you simply add the two fractions together. If they're not mutually exclusive, you add the two fractions together and subtract their what? 0.2. And subtract their what? Their and. If they're not mutually exclusive, we just call it the general rule of addition. You take the probability of the first event plus the probability of the second event, but then you have to take away the probability of where they overlap. There's the rules in general. Dice. I want to show this particular question. Says Laura's playing Monopoly. On her next move, she needs to throw a sum bigger than 8. A sum bigger than 8 on the 2 die in order to land on the property to pass go. Question, what is the probability that Laura will roll a sum bigger than 8? You see, a sum bigger than 8 doesn't mean a sum of 9 and a sum of 10, because you can't get a sum of 9 and 10 at the same time, can you? And a sum of 11 at the same time, and a sum of 12. That can't happen. So this is actually broken down by you. What does bigger than 8 mean? Well, it means the probability of rolling a sum of what? 9. What's my connector? Or the probability of sum of what? 10. Or probability of sum of what? And finally, or probability sum of 12. So within those one set of words, bigger than 8, we have a problem. It's this or this or this or. You have to be able to see that. Now I'm going to give you guys a little something. Show you this one thing with die. Okay, to learn. Look at what they got. The exact same thing. Okay? So this is an example of an or question that doesn't have the word or in it. You just have to know it is. Sum greater than 8 means 9 or 10 or 11 or 12. Okay. So, okay. I don't want you to look at this right now. What's the smallest sum when you roll 2 die? 2. 1 plus 1. What's the largest sum? 12. So that means you get a sum of 2, of 3, of 4, of 5, of 6, of 7, of 8, of 9, of 10, of 11, and 12. These are your sums. If you can remember this, this happens 1 time. This happens twice, 3 times, 4 times, 5 times, 6 times. And then it goes down 5, 4, 3, 2, and 1. Let's just talk what I'm talking about. Hey guys, if you have 2 die, and let's say one is red and one is white, If you get a 1 on the red and a 1 on the white, it's the same thing as getting a 1 on the white and a 1 on the red. That means it's only one instance. But this sum right here, okay, sum of 3, it happens twice. That means a red 2 and a white 1, or a white 1 and a red 2. That's 2 different instances. So if you can remember this, look how easy this question is. This question says, I want a sum bigger than 8. That means 9 or 10 or 11 or 12. This happens 4 out of 36 times. This happens 3 out of 36. The 11 sum happens 2 out of 36. And the sum of 12 happens 1 out of 36. 7, 8, 9, 10 out of 36. Take a 2 out, 5 out of 18. So if you can remember this little chart, it's only for one type of problem, rolling 2 dice and finding their sum. Going back to this example, that does it for this